Okay, welcome to Unit 3, Note Set 4. Remember, Unit 3 is on various effects, and the one thing that we're going to be talking about in this note set and several of the subsequent note sets is nonlinear effects. Now, yes, the compressor that we just looked at in Note Set 3 is a nonlinear effect, but I grouped that separately. Here we're talking about nonlinearity that occurs in guitar amps, primarily tube amps, as well as various distortion boxes that guitar players use to try to mimic or enhance the distortion characteristics of a guitar amp. Got a few readings here, the DAFX book, the Rice and McPherson book, but there's a really nice paper here by Pekarinen and Ye, which just kind of gives a review of some of these ideas. So I'm going to be drawing pretty heavily from this one as well as the other two a little bit. So let's talk about the family of nonlinear effects. We already talked about tube amplifiers, and I mean, to some extent, solid-state amps as well, although solid-state amps aren't as renowned as tube amps are for the sound that comes from their nonlinearities, but some modern recent versions of solid-state amps have tried to emulate the distortion characteristics of tube amps, so I suppose we should include that, but we're going to focus mostly on tube amps because that's where guitar players really think the good sound comes. And then some boxes that, some pedals that might provide some distortion, overdrive, and fuzz. And then we're not really going to talk about these, but I threw the phrase in here, exciters and enhancers. The DAFX book has a chapter on those, but I'm not covering it here. And like I said, compressors really should be included in this family, but I covered them separately in the previous note set. So let's talk about these three words: overdrive, distortion, and fuzz. And so guitarists make a distinction between these three words, although engineers think of all of them as just distortion. So an overdrive is an effect that guitar players view as producing some sort of warm sound and provide some overtones. And if you turn the volume of your guitar down, the overdrive decreases, that distortion decreases, and you get a clean sounding guitar. And then as you turn the volume up, you get a little bit more distortion. And then a distortion pedal is like an overdrive on steroids. So it produces a harsher sound, and it might not change its sound very much as you change the input signal level. It's going to change a little bit, but not that much. So much more distortion. So overdrive is more like classic blues guitar, and distortion is more like heavy metal type stuff. And then we have fuzz. So Jimi Hendrix was famous for perhaps introducing the fuzz, but I think there were some, well, I know there were some examples prior to that. So fuzz on I Can't Get No Satisfaction by the Rolling Stones, and some Kink Song, and Rocket 88, although I don't think that was created with a fuzz box. But a fuzz pedal is going to severely distort the signal, and pretty much no matter what you put into it, comes out looking like some sort of squarish wave. So it's a very severe sounding distortion. And it sounds like what its name says. It's kind of a fuzzy sounding guitar signal. So as I said, engineers group all of these as just distortion. So throughout this note set and others, if I may use the word distortion in an engineering context rather than a specific guitar-oriented context, but you can tell from the context which of those that I'm aiming for. So let's talk about nonlinearities and the distortion that they create, and what does that mean? So if you studied signals and systems, and you really should have if you're watching these videos and learning this stuff, you kind of need to have had a signals and systems class. And there you learned about a linear system, and you learned that if you put a single sinusoid in, you got a single sinusoid out. So here is a linear system. I'm putting sinusoid in, I'm getting a sinusoid out. And the only thing that changes is the amplitude. So we can see it went from an amplitude of 1 to something a little bit less than 1. And the phase shift. So we can see here that it crosses the 0 at 500, and here it crosses a little bit later. So there's a little bit of a phase shift there. And if we were to look at the spectrum, now this is a cartoonish version of it, should just be a delta function at the frequency of the sinusoid. That's just saying from a Fourier point of view that the sinusoids needed, the complex sinusoid needed to build a single sinusoid here is just a single spike, single frequency needed. So that's a linear system. Single sinusoid in, single sinusoid out, same frequency. If we put that into some nonlinear system, so now we're putting this single sinusoid into a nonlinear system. And you can see what I'm showing this nonlinear system to do. It's basically just clipping off the top. So that's a very characteristic type of nonlinearity. It's called a clip, or a clipper, or it's saturating or cutting off. Those are the kinds of terms that are used. And if you analyze, this is a periodic signal. So a sinusoid goes in and a periodic signal comes out of this. Periodic signal will be constructed by a fundamental frequency and a bunch of its harmonics. And here we're seeing that just the odd harmonics, so I don't know what this is, like maybe 161, something like that, but this is going to be 3 times that, and this is 5 times that. Now there are other nonlinearities where you'd get the even harmonics only, and there are other ones where you'd get both the even and the odd. But that comes clearly from a Fourier series point of view. But here's the thing. A nonlinear system creates other sinusoidal components when a single sinusoid goes in. So clearly not a linear system. So that's what we're talking about as a nonlinear processing of the signal. And the amount of distortion, we can see how it's distorted in the time domain, but we can also characterize the distortion by how much power there is in those extra frequencies that are added in. And those will always be harmonics if we put a single sinusoid in, integer multiples of the fundamental. So let's see why that happens. So we've got some nonlinear function. So we're only going to be considering systems for the moment here that have no dynamical nature to them. So not like an RC circuit where the output now depends on inputs from now and all past values as well. So that would be a system that has memory. So we say that an RC or an RL circuit has memory. But this is what's called a memoryless nonlinearity. The value that comes out at any given time depends only on the value of the input at that particular time. So here's the output of that nonlinearity with an x of t going in. So at the time t, the output depends only on the input at the time t. But it has the square of it and the cube of it and the fourth of it and so on. We see this from the idea of a Taylor series. In Calc 1, you learned that any function, well, there's some constraints on it perhaps, but any function that we'd be interested in here can be written out in a Taylor series. And back then we learned it without the of t. You just learned it as a function of x. But if we put in the of t and remind ourselves that the function depends only on the input at one specific time, we can use that Taylor series idea. So now suddenly we see that any nonlinear function that we're interested in can be thought of as, well, there's a constant term, there's a linear term, there's a quadratic, a cubic, a quartic, and so on and so on, with some appropriate coefficients out front that characterize the actual function that we're interested in. So let's see what happens when we put a sinusoid into such a nonlinear function. Well, we're going to get an A0, so we might get a DC offset when there is no DC offset going in, so that's an interesting new thing. We're going to get something proportional to the x of t, so if we put in cosine of omega 0 t, we'll get cosine of omega 0 t out as one of the terms with an A1 out in front. But now let's look at this term. It's going to be a cosine squared. And if you look at your trig identities, you'll see that we can rewrite that as a constant plus a sinusoid at twice the frequency of what went in. And likewise, we can write the cubic term. So this is that term with the sinusoid going in. And we get something at the original frequency and something at 3 times. And then for the fourth, we get a DC component, a doubling of the frequency and a quadrupling of the frequency. So if we went on, we would see that we keep getting these higher and higher integer multiples of this input fundamental frequency. And that's why we said on the previous slide, we get all these integer multiples. Now, each one of these terms is going to get multiplied by the characteristic coefficient that describes the particular nonlinearity that we have. But the bottom line is if we group all these together, we're going to have a bunch of DC terms together. We're going to have this thing together with that one. And we're going to have a doubling and those two combine. And there will be others down here as well that will be at 2 omega 0 t. So those all get combined together with the quarters and eighths and halves together with the A2 to create some coefficient, big A2, that multiplies the double frequency. And there's going to be some phase, because if you start adding sinusoids together, you can potentially get some phase shifts as well. And then we'll have all the 3s and all the 4s and so on. So in general nonlinear system, we put in something that looks like that. We're going to get potentially DC component, same frequency, double, triple, quadruple, quintuple, and so on. All the integer multiples of that. And so that's any nonlinear system that does that. We can describe this way will behave that way. Okay, so what happens if we put in a sum of sinusoids? And we're interested in this because we think of each individual note as being pseudo-periodic enough that we can sort of think about each individual note as being made up of a sum of harmonically related sinusoids. So if we put in a sum of harmonically related sinusoids, well, if we work out all the math, we'll see that we'll get sums and differences of all those input frequencies and a whole bunch more sums and differences of all those new frequencies as well. So we suddenly get a lot of different harmonics. So just as an example, suppose we added these two harmonically related cosines together into a square function. Okay, now we're going to get a doubling, a triple, a quadruple, and you can see that it's, the originals and sums of those and sums of those individuals, right? Because we get a 2 omega 0 plus a 2 omega 0 and so forth. So we get a lot of harmonic content when that happens. So lots of new structure. And believe it or not, in a musical setting, well, in some musical settings, distortion sounds horrible. And some of those distortions might not be very pleasing to the ear. So for example, if you are trying to design a nice audio amplifier, high fidelity audio amplifier, any distortion in that is going to sound bad. But guitar players figured out, at least at the high level, not necessarily the math level, but they figured out that the nonlinearities of tube amps, even though they were being designed to be used at lower volumes where they were linear, if you turned them up and you put in a large signal because you had your guitar turned way up and you turned the controls on the amp way up, the nonlinearities that resulted made the guitar sound, at least to some people, myself included, would sound great. And so suddenly amp designers started trying to make amps that purposely had nonlinearities in them and would distort in a very nice sounding way. So whether distortion sounds good or not depends on the application as well as your appreciation for the sound and what you're trying to accomplish. Now, we need models for nonlinear systems, and this is pretty much the most full-blown version of the model. And as usual, if we have a very complicated model, we may find it too difficult to use, and we might use some sort of simplified version of it. But it never hurts, even if you're going to use the simplified version, to at least have an idea of what the most general view is. And I don't know if this is the most general, but this is pretty much as complicated and general as most people get in describing these kinds of systems. So there is something called a Volterra series expansion. So Volterra was an Italian mathematician who was studying these kind of nonlinear functions, or nonlinearities applied to functions. He wasn't doing it for the purpose of audio because this was back in Fourier's day. But basically, we can say that we put a signal X into some nonlinear system, and we can think about it coming out as the output. And how does that go through? Well, remember, if we had just a linear system, we would get a term that looks like this. That's just convolution. So for a linear system, we would not have any of these. But for a nonlinear system, we have the convolution term plus some others. And let's look at this. Instead of an impulse response that's a function of one variable, we now have something that looks sort of like a generalization of an impulse response, but now it has two variables. And we're kind of convolving it simultaneously with two different versions of X, one shifted by V1 and one shifted by V2. So this is kind of a generalization of the idea of convolution. But look, we have an X times an X. So that's a quadratic dependence. So this H sub 2 captures the quadratic or the second order characteristics of this system. And then we have a three variable function, which we'll call H sub 3, and it operates on this cubic relationship. Now it's not X cubed, but there is a cubic relationship because, or a third order relationship, because X is multiplying itself 3 times. And so that captures the third order, and so on and so on. So when you see a diagram that looks like this, there is an impulse response. We know that this gets convolved with that. And now here is a generalization of that. We know that this thing is captured by that relationship, and so on and so on. And you can see dot, dot, dot. We go down as far as we need to go. At some point, theoretically, there will be infinitely many of these components. So we'd have infinitely many of these different orders. But at some point, those additional terms will be somewhat negligible. So we can truncate at some point and say that's a good model for this system. So that's the Volterra series expansion. So we're not going to go into the details of this, but it's nice to keep it in the back of your mind so that you kind of know, yeah, okay, that's really what's going on inside here. Now, it is possible to simplify this and to just simply run the signal through a bunch of different ordinary convolutions, and then the outputs of each of those convolutions goes through a first order, second order, all the way down to an nth order. So that's a modified version of the Volterra. And I need to point out that over here I put the superscript F. The superscript F means first. So the impulse response goes first. And notice that I didn't put the superscripts here. There really should be superscripts F's there to match these, but I didn't do that. Can we handle every Volterra system this way? I don't know. I don't know the answer to that, but I think that probably not. But can we handle a lot of them that way that might be of interest to us? Yes. And you should know that this H1 of F is not the same as this. And clearly this H2 superscript F is not this H2 because this has two variables and this just has one. But nonetheless, that's another way to think about it. Filtering and then running it through a power and then adding up all those terms. So that's a nice way to think about it too. Now, an interesting thing, we're interested in doing all this in discrete time. When we start dealing with nonlinearities in our systems, we have to be cautious about what our sampling rate is. So the sampling rate remains valid throughout a system as long as the bandwidth doesn't increase anywhere. And pretty much any linear system is not going to be able to really create extra frequency components that would cause problems with keeping the sampling rate the same. But let's look at nonlinearity. So first, let's see what happens in the continuous world. So we're going to apply a nonlinearity to a continuous time signal, and I claim that it increases the bandwidth. And that claim comes from a simple Fourier transform property that says multiplication in the time domain. So here is that multiplication, x times x, corresponds to something in the frequency domain that is a convolution. So it's a convolution between the Fourier transform of the signal and itself. So let's take a look. We know what this does in the time domain. At each instant of time, the value of x just gets squared. But let's take a look at what that does. So here's an example. Just pick a simple case where it's easy to see what happens. So suppose our signal x of t has a Fourier transform that looks like this, just a nice rectangular spectrum. You know what that looks like. That's a sinc function of some sort. And now we know that if we square that in the time domain, what do we get? Well, we get a sinc squared, and we know that a sinc squared transforms to a triangle. But we also know from this theory that the Fourier transform of x squared will be this thing convolved with itself. Now, at some point, you probably learned how to do convolution. Now we're doing convolution on a frequency axis, but nothing different. So you're going to flip one, slide it with respect to the other, and you probably learned that convolving a rectangle with a rectangle of the same width gives a triangle whose width is double the width of the rectangle. So now this thing goes from minus 2b to 2b. So look, we have higher frequency components. This one was band limited to b, and this one is now band limited to 2b. So if this one was sampled, let's just say we're sampling so that fs over 2 is just a little bit bigger than b. Well, now our fs over 2 for the squared one is there, and that means that this tail is going to flop back in because this thing is going to get moved out to be centered at fs. And there is aliasing that happens. So if we were to do this squaring on a discrete time version of this signal, we would get a spectrum in the discrete time world that does not look like this triangle. In fact, it would come down. So if this is fs over 2, it would come down to somewhere around here and then level out flat. So there's aliasing, and that might not sound good. It's not what we're trying to accomplish with a squaring. So that's a problem. So applying any nonlinear operation inside a discrete time system can and pretty much will create aliasing terms, and those are probably not going to sound good. So to avoid those, remember we studied multi-rate signal processing back in Unit 1, where we could upsample. Remember we stuffed L-1 zeros in, and then we used a filter, which I'm just showing as H1 here, to smooth out those zeros. That was our time domain view, or in the frequency domain view to suppress the image spectra that show up because of the stuffed zeros. Then we apply our nonlinearity with that higher sampling rate. So let's think about what that would mean. So at this point here, our sampling rate now might be out here, so that our Fs over 2, and maybe I should put a prime on that to show the sampling rate that's here after we've increased it. Now that's going to be all the way out here, Fs over 2, Fs prime over 2. No aliasing happens. So we apply the nonlinearity, and then we filter back down. So we apply a filter here, and we're throwing away that upper stuff, but remember that's probably outside of the range of our hearing. But what doesn't happen is that doesn't get folded back in and adding to there to create the aliasing. So we now filter and then decimate back down. So that's a nice scenario. So for a quadratic term, we'd only have to go up by 2. If we had a cubic term there, we'd have to go up by 3. And so, hey, back in our study of Volterra, suppose we determine that nth order is the highest non-negligible order that we have to include. Well, then that would mean that we would need to upsample by whatever that n is, and then we would downsample back by n. That's the idea. And this is actually done. If you look inside the snazzy devices that you can buy for doing nonlinear mimicking, discrete time mimicking of nonlinear processing, like guitar amps and things, the systems actually involve upsampling, applying the nonlinearity, and then decimating back down. And we'll talk about that either in this note set or the next one. I think it might be in the next one. So why are we doing all this nonlinearities in discrete time? Why do we want to do that? Remember, we're trying to mimic existing beloved analog circuits. So to understand what we need to do, we should understand a little bit about the nonlinearities that do occur in analog circuits. So, these nonlinearities occur in guitar amps, but they also occur in, overdrive boxes, distortion boxes, fuzz boxes, things like that. So that's what I'm referring to as these effects boxes that use some inherent nonlinearities to either mimic tube amps distortion. So then you can use the box followed by a nice perfect linear amplifier, and it would sound like you're going through a guitar amp. But sometimes people will take a nonlinear effects box and still run it into the nonlinearities in a guitar amp. So that's just enhancing those distortion characteristics. Now, perhaps the most well-known overdrive pedal is the Ibanez Tube Screamer, and you can see here's a whole bunch of different releases of that over the years. This was the original, came out sometime in the mid-1970s. Can't remember the exact date. You can go read about it at Electro Smash. They'll tell you a little bit about the history, and they'll tell you about the circuit that's inside that. But the Tube Screamer, or the TS-808 was the original model number. That was, and still is, kind of the most beloved overdrive pedal. And then we have a distortion box. And this is a pretty popular one, the Boss distortion DS1, DS being, I guess, for distortion. And again, you can go to Electrosmash and read all about it. And then we have the fuzz face, or a fuzz box. And this was one of the original classic fuzz effects. And again, Electrosmash will tell you all about it. So I would encourage you, if you're interested in this stuff, go over and learn how to analyze these circuits and understand what they're doing. So just a little bit, I'm just pulling off the schematic from the Electrosmash analysis of the Boss DS1 and just pointing out that there's a bunch of sub-circuits in there. We've got an input buffer, a transistor booster, an op-amp gain stage, and then here's really the heart of it. Diodes. There's two back-to-back parallel diodes there, and that's what's called a diode clipper. If you think about what's going on with the diodes, the voltage across that pair of diodes can never exceed that threshold voltage of a diode. So whether it be 0.6, 0.7-ish for silicon or something lower for germanium, that's the idea. It clips to that. So all of this stuff here is just getting the signal ready to be applied to this. So as you give more gain here, you're going to be more severely clipping the signal. But if you provide less gain here, you might just be barely clipping. In fact, the amount of gain that we have here might actually be an attenuation of the signal, but probably not. Guitar signals come in at about maybe 0.2, 0.3 volts peak, something like that at most, maybe 0.4 peak, something like that. So they do have to be boosted a little bit before the clipping actually even happens. And then got a tone control and an output buffer. So I'm not going to go into the details of all those other things, but head over to Electrosmash and you can read about this emitter follower here and the emitter follower here and a common emitter amplifier, classic circuits that you learned about in your electronics class, op amps, unity gain, and so forth. By the way, this diode here does nothing other than just protect that input. So it's not providing any kind of distortion. Distortion comes from there. But the important point here is diode clipping. In the Boss, it occurs here at the output of an op amp. And in the Tube Screamer, it appears here, again, back-to-back parallel diodes. And in the feedback loop of some beloved op-amp chip. People go crazy trying to find that particular chip to make the original Tube Screamer circuit. But that's the idea. So here we have a clipping stage, and here we have a clipping amplifier with the clipping in the feedback. But again, common emitter, so input buffer, output buffer. We've got a little bit of gain here with some tone control, a volume control, and then don't worry about this FET. That's just a switch to turn the signal flow on or off. So when it's operating, you can just view this as a straight through wire that's connecting there. So that's the idea. Where else can we have nonlinearities? Well, here's the circuit for a fuzz face. Again, head over to Electrosmash and check it out. But it's two cascaded transistors, and the original fuzz face was done with a PNP configuration. So a lot of modern day ones are still done with PNPs, and this AC128 was a very common transistor back then. They just grabbed them and put them in, but then people loved that particular sound, and so now today the AC128, it's a germanium PNP, no longer really made, but people will try to find old versions of those or find other transistors that are similar to them. But anyway, the nonlinearities come in because of transistors. They have inherent nonlinearities. And here's just a description, again taken from Electrosmash, showing the effect of this cascaded two transistor circuits, two transistor gain stages cascaded. And you can see that, here's the input, a sinusoid, and the output for just two different settings. It's really just distorting the signal to a large degree. The only difference is right here, right? On the other side, we don't see much difference. The other thing we see here is asymmetrical clipping or asymmetrical distortion, whereas the diode clippers will give you symmetric distortion. So those will give you two very different sounds, and that's part of why a fuzz face sounds the way that it sounds. Now, just a little reminder, here's a classic transistor circuit. Where is this nonlinearity coming from? Well, here is our VCE, so that's the voltage across collector to emitter, and here's IC, that's the current through the collector. And then as we vary IB, we move along these curves. So if you were to just fix VCE at, say, 6, and you were to fix, say, IB at 60 microamps, so you go up 6, 60 microamps, draw across that, you'd have 6 milliamps of current flowing in the collector. So now if we start putting resistors around this thing, as it's just sitting there with no signal attached, it's just sitting there biased to a certain point. It's like taking a teeter-totter. Here's the ground, and biasing it so that it is level, kind of in the middle of this range. And the resistors here, this RC together with this RL, will set this load line. And so now as we change IB based upon the input signal, this operating point will swing back and forth, and we'll get different currents going out, and the current through here will create a varying voltage there. So what ends up happening? Well, there's going to be some point where you make the input current large enough, and it's just going to go beyond where this thing can operate. And that's what's known as saturation. That would be the largest current that we can have flowing through here. Can't get any more, no matter how far up we go putting more IB in, we can't get anything more out. And then IB, as IB gets smaller, we're going to reach a point where we have cutoff. And so now the current just stops. And so that sets a range. If we make our voltage input too large, we're going to be making the swing up to saturation and down to cutoff, and we'll get some sort of clipping. So if we were to make this input bigger than what we show here, we would get this thing going up, but then clipping off, and then coming down and clipping off. And so that's the kind of distortion that we can get. And it's asymmetrical clipping that will occur because what's happening up here is a different geometry than what's happening down here on those curves. So that's the idea. Hopefully you've learned about something like this in your electronics class. By the way, if you are into electronics for guitars, great book to get. Check it out. Okay, so that's transistor circuits. Well, tube amp circuits are made out of tubes, and tubes are the precursors to transistors, and so we would expect there to be similar operations. Similar, but not the same. I've got this schematic. This is a schematic for an old Fender amp known as an 5F2A. That's the old Princeton Tweed back in the 1950s. This website offers you a lot of kits. You can go there and buy a kit, and you can build your own tube amp. They don't come with an awful lot of instructions, so you have to kind of know what you're doing in order to do that. But nonetheless, we've got tube circuits. There's a a triode. There's a triode, and there is a pentode that is a power tube. But they have their own inherent nonlinearity. So let's just look at a stage that looks like this. That's a triode amplification stage. We could analyze this very similar. If you're interested in more details, check out the book I just pointed you to. But we can analyze it in a very similar kind of way. And in fact, we can think about its curves, except its curves are not current driven. So actually no current goes in there. It's all driven by the voltage here relative to the cathode. And so as that changes, we're operating on different curves. So the VA is the voltage at the anode to the cathode. So if we were to fix that, say, at 100 and put VG at 0, we'd be operating at that point. Here's a decent bias point. So if we set this up so that when no signal is applied, we're operating at this point. So minus 2 volts here. And 225-ish across the plate or the anode to cathode. So we'd be operating there. And now as we put in an input signal, a sinusoid that goes in, that's the output. As we put in an input signal here, it's going to sweep us back and forth through these things. So that'll take us to these different points. And again, we can go up to the A point where things will pretty much saturate, and then we can go down to the C point where things will cut off. But as the input goes in, this thing's going to swing back and forth. And now you can see, look, these things are more widely spaced than these things. So there's going to be some asymmetry to this. And that's one of the things that makes the guitar or the tube amp sound the way that it sounds, is that asymmetry. And it also tends to have more of a soft clipping nature than the harsh saturation and cutoff that a transistor is going to have. And if you're interested in this, here's a good web page to go to. It's the Valve Wizard. The Valve Wizard's name is Merlin Blenko. Yeah, his first name is Merlin, and that's why he goes by the Valve Wizard. He's got this web page, but he's also got a bunch of books that you can buy and learn how tube amps work. But that's not what we are doing here. We're interested in mimicking these circuits in discrete time. So we can make a nice little digital signal processing box that's cheaper, lighter, costs less, weighs less, and has a lot more functionality, but should sound just like a tube amp. And people are doing that, and they've been doing it for quite a while. Now, I want to finish off this note set with some concepts that we'll be alluding to as we go through subsequent note sets. So these are different ways to approach finding the models for the kinds of systems that we're interested in. So they're just categorizing or characterizing different ways that we can find discrete time models based upon what we know and or what we're willing to do. So first, let's talk about the black box viewpoint. We treat the guitar amp, say, or a tube screamer box as just a box, and we don't know what's inside it. Even if we do know to some degree, we're going to ignore that in our attempts to find the models. And we're simply going to try to analyze the input and output relationships. If this input goes into this system and this output comes out, and this input goes in and this output comes out, knowing that, we might be able to deduce some discrete time nonlinear processing that we can put into our own black box that should mimic that. So the advantage of this approach is the solutions that come out of it are usually pretty low complexity because we're just kind of guessing as to what might be involved. And to be honest, this was one of the early approaches to this, and we'll talk about that more in the next node set. Today, I don't think that the black box approach, as it was originally employed, what is being done. But there is some more modern views of it where we literally put in inputs and measure outputs and let a computer deduce what should be inside the black box. In that case, it might not be so low complexity. We'll see more about that. Another disadvantage is that every time you change the knobs on your amplifier, different volume, different tone controls, the relationship between input and output is going to change. And so you really have to have multiple models. So even though each model has low complexity, you need to have a lot of low complexity models that can be adjusted. Now let's go to the other extreme. You can see I left a big hole there in the middle that we'll fill in just a minute. The white box approach. This is more along the lines of what people are doing today, although I did say that there is a premier version of black box out there today, and we'll talk more about that. But one approach to this that's a more modern approach is, look, we know what's inside these amplifiers. We have the schematics. I just showed you the schematic for an old Fender Princeton Tweed amp. We know what's in there. And we could also actually get some of these old amps. And so then we could measure and characterize from point to point to point to point. This little sub-block, right? We looked at this kind of thing. We've got one stage, we've got a tone control stage, we've got another amplification stage, we've got a power amp stage, we've got a power transformer stage, we've got a speaker stage. We could measure each one of those things and get a model, kind of a black box-ish model for each of those, and then combine those together as sort of a white box thing. So white box, you have complete knowledge of the circuitry that's inside, and you're going to try to model the components and the circuits. So people like Line 6, I think, tend to do this. Again, I've not worked at Line 6, so I don't really know how they do it. But from the wording in their manuals, they talk about how, we modeled this component, we modeled this stage, we got inside the amp and analyzed it, and they have all the schematics. So the disadvantage is there's an awful lot of complexity to deal with. You might be modeling all the way down to resistors and capacitors and tubes and so forth. But the advantage is that those models will be parameterized. So you don't have to have different models for every different knob setting. You just have a model that is parameterized. Now, what's in the middle? Gray box. You might not know everything that is in the circuit. We might not have complete knowledge of the circuitry, but we've got some idea of what's in there. So we've got a structural knowledge. So we might know that for this particular amp, there's this many stages of gain, and we might know that that consists of a preamp, then a volume, then a preamp, then a tone, and then some other tube stages known as phase inverters and power stages. And so the goal here is sort of to fit between the black box and the white box and get some of the advantages of both and try to mitigate disadvantages of each of them. So that's the idea. So as we go through these things, I'll kind of point out where we're talking about in this spectrum, but keep that in mind as you think about other things that you might be interested in. So the last thing in this note set that I want to talk about is this idea of interpolation. This is handling the fact that we said back here that we need multiple models, one at each knob setting. Well, how many different knob settings? So each knob might go 1 to 10. So maybe you set it at 1, you set it at 2, you set it at 3. Well, what if you want it at 1.5? Well, now you need to interpolate between your models. And so how you do that interpolation is a big deal. So you've got this lookup table of model parameters, and then you interpolate between them. So it can still lead to an awful lot of memory that you have to store all these things. And so therefore, it might be worthwhile to try to figure out how to reduce the size of all these tables. And so some sort of interpolation scheme, if you can come up with an interpolation scheme that says, you know, I don't really need it at 1, 2, 3, 4. Maybe I just need it at 2 and 4 and 6, things like that, and you can interpolate. So it's interesting that many of the early patents in this field focused more on the interpolation aspect than on actual better ways to model the amps. So in the next set of notes, we'll start looking at some of the early ideas used to model guitar amps and nonlinear effects. And then after that, we'll start getting into a lot more details of, you know, more like a white box approach. And then we'll finish off this unit with, you know, kind of a blackish, grayish approach that just sticks a bunch of signals into the amplifier and measures the output and somehow uses those to deduce what you should put in your DSP processing to mimic that amplifier. So hopefully I'll see you in the next note set.